Imagine, for a moment, that you are adrift, not on any ocean, but in the silent, velvet blackness of deep space. The stars around you are no longer sharp points of light, but soft, distant smudges, like forgotten embers. You feel a gentle, almost imperceptible pull, a current in the cosmic sea, drawing you toward a patch of darkness unlike any other. This is not the simple absence of light between stars. This is a void, a perfect circle of nothingness, so profound it seems to cut a hole in the very fabric of reality. As you drift closer, a strange and beautiful halo begins to form around its edge. A ring of light, captured starlight, twisted and warped into a luminous crown. This light is a final, desperate message from a universe that is being consumed. It illuminates the edge of the abyss, the shore of an ocean from which no traveler returns. This is the event horizon. It's not a wall, not a gate, but a threshold, a line drawn in space-time where the pull of gravity becomes absolute. To cross it is to surrender to a one-way journey into the heart of forever. Long before we had a name for it, humanity sensed its presence. We told stories of star-eating serpents, of celestial whirlpools that swallowed light and gods alike. Ancient myths whispered of gates to the underworld, cosmic maws hungry for creation. Were these just stories, or the echoes of a fundamental truth our ancestors felt in their bones? That somewhere out there, the universe had a mouth. In the 18th century, thinkers like John Mitchell and Pierre-Simon Laplace dared to imagine this scientifically. T spoke of dark stars, so massive that their own gravity would trap their light, rendering them invisible. It was a staggering idea, a ghost in the elegant machinery of Newton's universe. For over a century, it remained a curiosity, a mathematical phantom. But then, a new kind of thinking emerged, one that reshaped our entire understanding of the cosmos. Albert Einstein didn't see gravity as a force pulling objects together, but as a curvature in space and time itself. Imagine a heavy ball placed on a stretched sheet. It creates a dip, and other, smaller objects roll toward it. Einstein's theories suggested that something massive enough could create not just a dip, but an infinitely deep well-a-puncture. In spacetime, a place where gravity is so strong that the universe folds in on itself, and the rules as we know them cease to apply. For decades, even Einstein himself resisted this final, terrifying implication of his own work. A singularity, a point of infinite density, seemed too strange, too extreme to be real. These dark stars were mathematical monsters, confined to the pages of theory. Yet, the universe is often stranger than we can imagine. Telescopes began to turn toward the heavens, searching for whispers and shadows, hunting for evidence that these cosmic leviathans were not just equations, but a real and vital part of our cosmic story. Out in the distant dark, far from the comfortable glow of our own galaxy, colossal stars live out their brilliant, violent lives. These cosmic giants, hundreds of times more massive than our sun, burn through their fuel in a blaze of glory. They are the forges of the universe, creating the heavy elements that make up planets and even ourselves. But for the most massive of these stars, their magnificent end is not a quiet fade into darkness. Their death is a cataclysm of unimaginable scale, an event that gives birth to the very objects of our story. We are now drifting toward such a stellar nursery, a place where a giant is on the verge of collapse, about to ignite a fire that will leave behind only a shadow. For an eon, it held the darkness at bay, a brilliant lighthouse in the cosmic ocean. Now, that age is ending. Deep within its heart, the forge that powered 1 billion years of light is sputtering. The hydrogen, once an endless fuel, is gone. Helium, then carbon, then heavier and heavier elements have been its sustenance, each burning faster, hotter, more desperately than the last. Each stage a shorter, more frantic breath against the inevitable. Now, it has come to iron, a heart of cosmic ash. Iron is the end of the line. Fusing, it consumes energy, rather than releasing it. The star's furnace, which held gravity in a delicate, millennia-long dance, has gone cold. The outward push of light and heat falters. For the first time in its long life, gravity begins to win. The balance is broken. There is no sudden bang. Not yet. Just a quiet, inexorable squeeze. The immense outer layers, trillions upon trillions of tons of incandescent gas, now press down with unimaginable force. The pressure that held them up for ages, the electron degeneracy pressure, is like a dam facing an ocean that has suddenly decided to fall from the sky. It holds for a moment, a fraction of a second, a defiant last stand against physics. But the star is too massive. The dam breaks. The core collapses. In less than a second, a sphere the size of a planet implodes into a city-sized knot of matter. The collapse is so violent, so absolute, that the outer layers, which were just beginning their fall, suddenly hit a wall of impossibly dense material and rebound. A shockwave of unimaginable power erupts outwards. A silent scream of light and energy. This is the moment ancient skywatchers recorded in their chronicles, a guest star suddenly blazing in the heavens, bright enough to be seen in daylight. They wove tales of phoenixes, of gods dying and being reborn in fire. They weren't entirely wrong. The star is dying, yes, but in its death, it seeds the universe. The shockwave is a celestial tsunami, forging gold, platinum, and uranium in its fury and flinging them across the galaxy. Every atom of gold in a wedding ring, every bit of silver in a coin, was born in a moment just like this. The shockwave tears the star apart. It's beautiful. Glowing layers are blasted into space, forming a magnificent, expanding nebula. Ghosts of light and color. But for a star this massive, something else remains. Had it been a little smaller, the collapsed core would have held as a neutron star, a city-sized atom of mind-boggling density. But this star was a true giant. Its gravity is too powerful, even for that. The collapse continues. Nothing can stop it now. The core shrinks past the point of no return, crushing itself out of existence. It folds space and time in on itself, wrapping itself in a shroud of its own gravity. The escape velocity at its surface surpasses the speed of light. The star is gone. In its place, a perfect, silent darkness is born. The newborn black hole is a ghost, veiled by the drifting, shimmering debris of its own violent birth. The last echoes of the supernova's light play across the event horizon, that invisible border from which nothing can ever return. The chaos settles, the debris cloud thins, a cosmic mist revealing not a new star, but a new kind of geometry, a warp in the very fabric of spacetime, a quiet, patient well in the cosmos, waiting. And so, we feel it now, the subtle dip, the gentle curving of spacetime beneath us. It's not a force pulling us, not in the old Newtonian sense. Instead, the very fabric of the universe is changing shape. Imagine a vast, flexible sheet, stretched, taut. Where we are, it's almost flat. But ahead, where that point of perfect darkness hangs, the sheet is being pulled down into an impossibly deep well. This is Einstein's vision of gravity. Not a tug-of-war between objects, but the landscape of reality itself. Warped B-mass, that darkness is a place of extreme gravity, so extreme that it has created a pit in the fabric of spacetime, and we, like marbles rolling on this curved surface, are not being pulled, but are simply following the straightest possible path through a bent reality. Our trajectory is no longer a straight line, but a gentle, sweeping curve, drawing us ever closer to the edge of that pit. It's a concept that a mathematician named Carl Schwarzschild first solved, giving us the first glimpse into the geometry of this strange new object. He showed us the numbers behind the abyss. Now, as we drift, let's consider time itself. Here, in this gentle, gravitational slope, our clocks are already beginning to disagree with those far away, in the flatter regions of spacetime. The closer you get to a massive object, the slower time flows. It's a phenomenon called gravitational time dilation. Think of it like a river. Far upstream, the water flows at a steady, even pace, but as it approaches the precipice of a great waterfall, the current quickens, rushing faster and faster. For an observer standing safely on the riverbank, a leaf caught in that current would appear to speed up as it nears the edge. But now, imagine you are Asterisk, On asterisk, that leaf, from your perspective, it's the riverbank that seems to be whizzing by. It's all relative. With gravity, it's the opposite. The deeper you go into the gravitational well, the slower your clock ticks, relative to someone far away. Time itself is being stretched. So, if we were to send a probe ahead of us, one with a brightly flashing light that blinks once every second, what would we see? As it falls toward that dark edge, we would see the flashes get further and further apart. A second for the probe would become 2 seconds for us, then a minute, then an hour. The light from its flashes would also become redder, stretched to longer wavelengths by the intense gravity it's trying to escape. From our vantage point, we would watch its journey slow to an agonizing crawl. It would appear to freeze, hovering just at the edge, its light reddened into infinity, fading but never quite disappearing. It would seem to be eternally stuck at the boundary. This boundary has a name. The event horizon. It's not a physical surface you could touch. It's a one-way door, a threshold in spacetime. It's the point of no return. In myths and legends, there are always doorways that change those who pass through them, thresholds from which you cannot come back the same. The event horizon is the cosmos's ultimate version of this. Once you cross it, the path forward is only one way. Down, the curvature of spacetime becomes so extreme that all possible paths, even the path of light, lead to the center. Looking ahead, we notice something else. The light from stars and galaxies far behind the black hole is being distorted. It's as if we're looking through the base of a giant wine glass. The gravity of the black hole is so immense that it bends the path of light, acting as a cosmic lens. This is gravitational lensing. For certain alignments, we might even see the light from a single star bent into a perfect circle, an Einstein ring, encasing the darkness. This is the origin of the famous shadow of a black hole not the hole itself, but the silhouette it casts against the light it has so profoundly warped. We drift closer. The silence of space is not so silent here. There's a hum, a whisper of energy. It's the sound of photons and particles that have been journeying for billions of years, only to find their voyage ending here, in this gravitational embrace. They are not falling in a straight line, but are being whipped around, forming a chaotic, glowing disk of superheated matter, a brilliant ring of light and energy that will soon become our entire world. We are approaching the accretion disk, the last fiery gasp of matter before it crosses the threshold forever. We've looked into the darkness, into the silent heart of a black hole where space and time bend into an eternal knot. But not all is quiet at the edge of this abyss. Around many black holes, a storm of unimaginable fury rages, creating some of the most spectacular light shows in the entire universe. This is the realm of fire rings and lightning jets. Imagine a vast cloud of gas and dust, perhaps the remains of a star that wandered too close. As it's pulled in by the black hole's immense gravity, it doesn't just fall straight in. Instead, it begins to spiral, accelerating faster and faster, like water circling a drain. This spiraling material flattens into a massive, rotating structure called an accretion disk, and this is where the fireworks begin. The matter within the disk is moving at incredible speeds. Different layers rub against each other, creating immense friction. This friction heats the gas to millions of degrees, causing it to glow fiercely, not just in visible light, but in high-energy The accretion disk becomes a cosmic forge, a blazing ring of fire encircling the black hole's shadow. In our own Milky Way, we see this phenomenon in what are called X-ray binaries. A star and a black hole locked in a celestial dance, with the black hole siphoning material from its companion, feeding its brilliant, hot disk. But this cosmic engine can do more than just glow. The intense heat and motion within the accretion disk generate powerful magnetic fields. These fields become twisted and tangled by the disk's rapid rotation. Now, if the black hole itself is also spinning end, most are it drags the very fabric of spacetime around with it, a phenomenon known as frame dragging. This interaction between the spinning black hole and the magnetic fields of the disk creates a cosmic dynamo of staggering power. In a process we're still working to fully understand, this dynamo can grab a portion of the infalling matter and fling it outwards, away from the black hole, at nearly the speed of light. These are relativistic jets, colossal beams of energized particles, like cosmic spears of lightning. They can travel for hundreds of thousands, even millions of light. They're so powerful they can punch clean through the galaxy that hosts them. It was our curiosity, our drive to see the unseen, that first revealed these incredible structures. When we built radio telescopes in the mid-20th century, we opened a new window on the universe. We suddenly saw these enormous lobes of radio emission extending far beyond the visible confines of distant galaxies. We were seeing the ghostly afterglow of jets that had been launched from a central black hole millions of years earlier. And when we look back toward the dawn of time, we see the most extreme examples of this process. These are not just any black holes. They are supermassive giants in the hearts of young galaxies, feeding voraciously. Their accretion disks and jets are so luminous, they outshine their entire host galaxies by thousands of times, appearing as brilliant, star-like points of light across billions of light. These ancient beacons, fueled by the same physics we see in our own cosmic neighborhood, were the lighthouses of the early universe. From the swirling, incandescent disk to the focused, galaxy-spanning jet. The area around a black hole is a place of creation as much as destruction. It is an engine that transforms the raw stuff of the cosmos gas and magnetic fields into colossal structures of energy and light. These forces don't just operate in isolation. They reach out, influencing the birth of stars and shaping the evolution of the very galaxies they inhabit. And at the heart of it all, in the centers of most galaxies, including our own, lie the ultimate versions of these cosmic engines. Have you ever stood in the heart of a bustling city at night, feeling the hum of its energy, the countless lives swirling around a central point? Our galaxy, the Milky Way, has a heart just like that. A downtown district where stars are packed 1,000,000 times denser than in our quiet suburban neighborhood. If you could look towards the constellation Sagittarius with eyes that see in radio waves, you'd witness a spectacle of stellar orbits, a frantic, beautiful dance. For decades, astronomers watched these stars, like fireflies trapped in a cosmic jar, whipping around a point of utter blackness. They moved so fast, completing orbits in just a few years, that they could only be responding to an immense gravitational pull. The math was undeniable. Squeezed into a space smaller than our solar system was a mass 4 million times that of our sun. There was nothing there to see. Just a void. A gravitational ghost. This was our first confirmed glimpse of Sagittarius A*, the supermassive black hole at the center of our galaxy. It's the hearth of our cosmic city. A place of both immense power and quiet mystery. Watching these stars trace their elliptical paths was a triumph of patience. It required teams of observers on mountaintops, coordinating observations over many years, battling weather, timing their exposures to the Earth's rotation, all to piece together this invisible portrait. It was like trying to map the floor plan of a darkroom by watching the dance of dust motes in a single sunbeam. And from that dance, they knew something colossal was hiding in the shadows. But to truly see one of these behemoths, to look into the abyss, required something even grander. It required a telescope the size of our entire planet. This wasn't a single dish, but a global network of observatories, from the peaks of Hawaii to the deserts of Chile, all synchronized by atomic clocks. All pointed at the same target 55 million light-years away in the galaxy. Messier 87. This was the Event Horizon Telescope. For years, they gathered data, a deluge of information shipped on hard drives, because it was too vast to send over the internet. And then, in 2019, the world saw it. Not the black hole itself, but its silhouette, its shadow cast against the glowing, superheated gas swirling into it. A perfect ring of light, brighter on one side where the material was spinning towards us, surrounding a circle of pure black. This was the event horizon of M87*, a monster weighing 6.5 billion times our sun. It was the eye of the cosmic hurricane, the point of no return made visible. It was a photograph of gravity itself. These galactic hearts are not just passive anchors. They are active engines that shape their entire galaxies. As matter falls toward a supermassive black hole, it doesn't just vanish. It forms a superheated accretion disk, a spinning platter of plasma hotter than the core of a star. This disk can launch colossal jets of energy, lighthouse beams that blast out from the galactic center for hundreds of thousands of light. These jets and the powerful radiation from the disk act like a cosmic thermostat. They can heat up or blow away the vast clouds of cold gas that would otherwise form new stars. This process, called feedback, is a delicate balance. The black hole's hunger can quench star formation, preventing a galaxy from growing too large. It acts as a regulator, a shepherd for the flock of 100 billion stars. In this way, the heart of the galaxy, this fearsome, dark engine, nurtures its home by keeping its own growth in check, shaping the very structure and evolution of the cosmic city it resides in. So we stand on the outside, looking in. We see the orbits of frantic stars. We see the shadow cast by an event horizon. We see the feedback that sculpts galaxies across cosmic time. Everything we observe is a consequence of what lies within, the gravitational echo of an unseen reality. We have mapped the doorstep, but what lies beyond that threshold? What happens inside that region of space from which not even light, not even information, can return to us? We have seen the shadow on the wall of the cave, but what is the nature of the object casting it? What reality exists past the point of no return? We are hovering at the edge, the very brink of forever. Below us, the universe warps into a silent, perfect circle of nothing. This is the event horizon, the point of no return. The laws of our familiar world bend and blur here, but they do not yet break. We have traveled far, guided by the mathematics of Einstein, to this place where space and time become something else entirely. Now, let's take the final step. Not with a ship, but with our minds. Let's cross the line. The instant we cross, what? The way. For a truly colossal black hole, millions or billions of times the mass of our sun, Tian Sweries, nothing. Absolutely nothing. There is no cosmic doorbell, no shimmering curtain to pass through. From our perspective, what physicists call our proper time, the journey into the black hole begins without any drama. The clock on our wrist ticks on just as it always has. We are falling, yes, but we have been falling all along. The transition is seamless, utterly uneventful. Why is this? It's a matter of scale. The immense gravity of a supermassive black hole is spread out over such a vast area that its gradient is gentle at the horizon. The dreaded spaghettification, that terrifying stretching force that pulls you apart atom by atom, is certainly waiting for us. But for now, it's far, far below, deep in the heart of the abyss. Here, at the edge, the tidal forces are weaker than those you might feel on Earth. We are intact. We are still US. But while our personal experience of time feels normal, for anyone watching from the outside, our story is very different. To them, as we approach the horizon, our image would have slowed, stretched, and reddened, freezing for an eternity on the boundary, never quite crossing. An observer's coordinate eye sees us locked at the edge forever. But for us, Tian flows onward, carrying us deeper. We have slipped out of their universe and into a private, one-way future. Looking forward into the black hole, we see nothing unusual. The light from stars that fell in before us continues its journey inward, so we don't see a wall of blackness ahead. But looking back, that's where things get strange. The view of the entire universe we left behind is now compressed into a shrinking window of light above us. The whole future history of the cosmos plays out in that window, accelerating faster and faster, like a movie on fast forward, until it all blue shifts into a brilliant final flash. We are now riding a current not of water, but of space-time itself. Space is flowing, pulling everything inward, toward the center at, and then beyond, the speed of light. There is no fighting this current. Turning on our most powerful engines would do nothing. Every possible direction we could point, every path we could take, now leads to the same place. The singularity. The future is no longer a direction in space. It is a destination in time. What does the geometry of this new reality look like? The equations that describe this place, when pushed to their logical limits, hint at bizarre possibilities. They sketch out maps like the Kruskal-Shika's diagram that suggest our universe might be connected to another, a white hole from which matter can only exit. They even draw paths for theoretical wormholes, tunnels through spacetime. These are the ghosts in the machine of general relativity. Beautiful mathematical artifacts that may or may not correspond to physical reality. They are the underworld myths of modern physics, whispers of other realms, just beyond our grasp. But as we fall, a profound and unsettling question begins to form. We are made of atoms, energy, and something more subtle. Information, the specific arrangement that makes you asterisk. You asterisk. The story written in your DNA. The memories in your mind, all of it is information. According to the laws of quantum mechanics, information can never truly be destroyed. It can be scrambled, hidden, or rearranged, but it cannot be erased from existence. Yet here we are, on a one-way trip to a singularity, a point of infinite density, where the laws of physics are thought to break down completely. What happens when we arrive? What becomes of the intricate, unique pattern that is us? Does it vanish forever, violating one of the most fundamental principles of the cosmos? Or does it somehow escape? This is the paradox, the deep conflict between our two great theories of the universe. As we drift in this river of space-time, suspended between a frozen past and an inescapable future, everything we are, everything we were, comes down to that single, haunting puzzle of information. And imagine, for a moment, the absolute quiet at the edge of everything. We're not in the roar of a collapsing star anymore, but in the deep, humming silence just outside a black hole's event horizon. This isn't empty space. It's a fizzing, seething quantum foam. Here, the laws of physics whisper that something extraordinary is happening. In this quantum realm, pairs of particles are constantly winking into existence and then annihilating each other in a flash. There are virtual particles, a sort of energy loaned from the universe that gets paid back almost instantly. But what happens if this particle pair pops into existence right on the brink of the event horizon? Picture two twins, born holding hands at the edge of a waterfall. Suddenly, one slips over the edge, while the other just manages to hang on. The one that falls in is doomed, pulled into the singularity. But the one that escapes, it has no partner to annihilate with. It becomes a real particle, flying away from the black hole. To an outside observer, it looks like the black hole itself is glowing, emitting a faint thermal radiation. This is Stephen Hawking's revolutionary idea, Hawking radiation. But there's no free lunch in the universe. The energy for that escaping particle has to come from somewhere. It comes from the black hole itself. The particle that fell and carries negative energy, effectively reducing the black hole's mass. This means, over unimaginable timescales, black holes are not eternal. They evaporate. They shrink, particle by particle, until they vanish in a final puff of radiation. This gave rise to another profound concept. If a black hole has a temperature, as Hawking showed, it must also have entropy, a measure of disorder or information. Jacob Bekenstein had argued this years earlier. He proposed that the entropy of a black hole isn't related to its volume, but to the surface area of its event horizon. It is like a library, where all the information of the books it swallowed is stored on the shelves inside, but is somehow written in its entirety. On the library doors, every star, every planet, every bit of matter that falls in, adds to the information content inscribed on this cosmic boundary. But this elegant picture leads to a terrifying problem. The information paradox. A fundamental rule of physics is that information can never truly be destroyed. It can be scrambled, burned, or shredded. But in principle, you could always piece it back together. If a book is burned, you could theoretically reconstruct its words from the ash and smoke. But when a black hole evaporates, what happens to the information it swallowed? Hawking's initial calculations suggested it was gone forever, erased from the universe. This is a physicist's nightmare. It would mean our understanding of reality is fundamentally wrong. All the unique details of what fell and the difference between a star and a spaceship would be reduced to a uniform thermal assay. This is where physics stands, teetering on a knife's edge. To resolve this, some of the most brilliant minds have proposed even stranger ideas. One is the holographic principle. It suggests that maybe Bekenstein was more right than he knew. Perhaps all the information about what is inside the black hole, the three-dimensional reality, is indeed encoded on its two-dimensional event horizon, like a hologram. The falling particle doesn't destroy information. It just adds to this holographic projection on the boundary. When the black hole evaporates, the information is slowly released back into the universe, encoded in the subtle correlations of the outgoing radiation. It has a concept that stretches the imagination to its limits. A universe where reality is etched onto a distant surface. We're left with this profound, unsettling question. The memories of a star. The story of a civilization, are they truly lost? Or are they just written on a threshold we can't yet read? Is the information paradox a dead end, or a doorway to a new kind of physics? It forces us to wonder. How could we ever know for sure? How do we listen for the whispers of a dying giant and read the story it tells? For millennia we've looked to the heavens for omens, for signs from the gods. Reading stories in the stars, we saw hunters, queens, and mythical beasts. But for all our gazing, the universe had a secret language. One spoken not in light, but in vibrations, in the very fabric of reality itself. And on September 14th, 2015, for the first time, we heard it speak. It began as a quiet chirp, a sound lasting less than a quarter of a second. It wasn't heard by ears, but by two colossal instruments in Washington and Louisiana. The Laser Interferometer Gravitational Wave Observatory, or LIGO. For years, scientists had waited, listening for the faintest whisper from the cosmos. They sat through long night shifts, fueled by coffee and sheer determination. Sifting through endless noise for a signal, they checked and rechecked their data, wrestling with error bars and the constant fear of a false alarm. But this was real. The chirp was the sound of a symphony 1.3 billion years in the making. It was the final, frantic spiral of two black holes, each about 30 times the mass of our sun, as they danced towards a cataclysmic merger. In that final fraction of a second, as they collided and became one, they unleashed an amount of energy so immense it shook spacetime itself. These ripples, these gravitational waves, traveled across the universe at the speed of light, growing fainter and fainter until they washed over Earth, minutely stretching and squeezing everything they passed through, including LIGOs. 4-kilometer-long arms. The sound we detected, that chirp, was the song of their union. By analyzing its rising pitch and volume, we could weigh the black holes, measure their spin, and confirm that Albert Einstein, a century earlier, had been right. The universe really did sing. Hearing the universe was one thing. Seeing its most elusive ghosts was another. This required a different kind of oracle, a planet-sized eye. The Event Horizon Telescope wasn't a single instrument, but a global network of radio telescopes, from the mountains of Hawaii to the deserts of Chile, from Spain to the South Pole. They all had to point at the exact same spot in the sky, at the exact same time, recording an avalanche of data. For years, astronomers coordinated these observations, battling weather, technical glitches, and the sheer logistical nightmare of it all. They flew hard drives too much data to send over the internet to central processing centers. And then, after painstaking work, combining the signals, correcting for atmospheric distortion, and running complex algorithms, the first light emerged, not the light of a star, but the shadow of a monster. There it was. The silhouette of the supermassive black hole at the heart of the M87 galaxy, 55 million light-years away. We saw a ring of glowing, superheated gas swirling around a perfect circle of blackness. The Event Horizon, the point of no return. We weren't just testing theories anymore. We were mapping the edge of reality. Yet, even these triumphs only scratch the surface. The universe still whispers its secrets in other ways. X-ray telescopes like Chandra stare into the hearts of galaxies, watching as matter is ripped apart and heated to millions of degrees before it vanishes into a black hole, giving off a final, brilliant scream of high-energy light. And sometimes, we find them by their absence, through a subtle trick of light called microlensing, where a passing object's gravity briefly magnifies a distant star. We've found hints of solitary, wandering black holes, drifting silently through our own galaxy. They are the true ghosts in the machine, detectable only by their fleeting gravitational influence on the light around them. Each detection, each faint signal pulled from the noise, is a revelation. The ancient oracles read the entrails of animals, or the flight of birds, to divine the future. Today, our instruments read the faint tremors in spacetime, and the distorted light from distant galaxies. We have replaced mythic omens with data, superstition with spectroscopy, and yet the sense of wonder remains. Every time we answer a question how black holes merge, what an event horizon looks like, where they might be hiding, we find ourselves standing before a dozen new, deeper questions. The darkness isn't empty, it's just quiet, and we are only just beginning to learn how to listen. Each new signal, each new image, is not an end to a mystery, but an invitation into a larger one. We stand now on a shore of shadows, looking out not at a known ocean, but at an abyss of cosmic speculation. The familiar lighthouses of established physics grow dim behind us, and ahead, the water is dark, deep, and filled with rumors. This is the frontier, the place on the map where ancient cartographers would write here be dragons. For us, the dragons are questions, monstrous in their size and complexity, yet irresistible in their allure. What if the dark matter that holds our galaxies together isn't some exotic, undiscovered particle, but something far stranger and more familiar? What if it's a sea of primordial black holes, born not from collapsing stars, but from the violent, dense chaos of the Big Bang itself? Imagine countless tiny singularities, each no bigger than a grain of sand but as massive as a mountain, scattered through the void like a fine, dark dust. They don't shine, they don't interact, they just asterisk. Our asterisk their gravity, the invisible skeleton upon which the universe we see is built. We haven't found them yet, but we're looking, listening for the faint, temporary brightening of a distant star as one of these phantoms drifts by, bending its light for just a moment, a cosmic ghost in the machine. And then there are the true leviathans. We've spoken of supermassive black holes, but whispers are growing of something even more colossal. Ultramassive black holes, objects tens of billions of times the mass of our sun, so vast they defy our current models of galactic evil. How do such monsters form? Do they grow by an insatiable diet of gas and stars, or do they represent the direct collapse of unimaginable clouds of primordial gas in the early universe? They are the cosmic krakens, lurking in the centers of the most massive galaxies, their sheer scale a challenge to our understanding of cosmic limits. Beyond the galactic cores, we suspect there are wanderers. Stars are ejected from their birthplaces all the time. Why not black holes? Imagine a black hole, the mass of a star, silently roaming the interstellar darkness between solar systems, invisible and untethered. Our only hope of finding these solitary pilgrims is through microlensing, the same technique we hope to use for primordial ones. A chance alignment, a flicker of starlight, and suddenly we'd have proof of these lonely, nomadic titans. How many are out there? 100 million in our galaxy alone. 1 billion. We simply don't know. They are the rogue waves on the cosmic ocean. Their existence probable. Their numbers a mystery. To see these new dragons, we need new ships, new maps. We are building them. The Laser Interferometer Space Antenna, LISA, will be a gravitational wave observatory in space. A triangle of satellites millions of kilometers on a side, listening not for the crash of stellar mass black holes, but for the slow, gentle hum of supermassive ones merging. A bass note echoing across billions of years. The next generation Event Horizon telescope will sharpen our vision, promising not just a clearer picture of a black hole's shadow, but perhaps even movies of the matter swirling into oblivion, a real-time voyage to the edge of the abyss. And as we approach this final horizon, the fabric of spacetime itself begins to feel strange. The most daring explorers of theoretical physics are sketching new charts, whispering of connections that sound like magic. They speak of RE=E, PRA mind-bending conjecture, suggesting that two entangled particles, linked across any distance, might actually be connected by a wormhole, a bridge through spacetime. This idea hints that the very geometry of space and time isn't fundamental. It might be an emergent property woven from the quantum entanglement of countless particles. Spacetime, in this view, is not the stage. It's part of the play, a shimmering illusion created by a deeper quantum reality. We are sailing into a fog of profound uncertainty. The familiar laws of physics are the wind in our sails. But ahead, the very nature of space, time, and reality seems to be up for debate. The sea serpents on our maps are no longer just monsters. They are signposts pointing toward a new kind of physics, a deeper understanding of existence. The edge of knowledge is not an end, but an invitation. The abyss is not empty. It's filled with the promise of discovery, a dark ocean murmuring with the secrets of everything, and we are just beginning to learn how to listen. Here we are, at the quiet edge of everything we've explored together. We've journeyed from the first whispers of a collapsing star to the deafening silence at the brink of an event horizon. We've wrestled with warped time, stretched space, and the profound, beautiful paradoxes that black holes represent. This wasn't just a tour of cosmic phenomena. It was a journey into the heart of human curiosity itself. For centuries, we have stood at the shore of a vast, dark ocean, drawn to the unknown. Black holes are the ultimate expression of that frontier, a place where our most trusted laws of physics surrender, and where the language of our universe changes into something we are only just beginning to decipher. They are not just celestial objects. They are gravitational poets, shaping galaxies with their immense presence, sculpting the starscapes we see, and in turn, shaping our ideas about reality. The event horizon, that point of no return, is more than a physical boundary. It's a symbol of the limits of our knowledge. Standing at its edge, we are reminded that for all we have discovered, for all the equations we have written, the universe still holds its greatest secrets close. But it's this very mystery that fuels us. It doesn't discourage us. It inspires us. It's the engine of science, the reason we build greater telescopes, devise bolder theories, and continue to ask, what if? Right now, science stands at a fascinating crossroads. We have theories, some elegant, some wild about what lies beyond the horizon. Is it a singularity? A point of infinite density? A gateway to another universe? Or something so strange our current minds cannot even conceive of it? We don't have the final answer. And perhaps that's the most honest and exciting thing we can say. The story of black holes isn't finished. It's an open question, whispered across the cosmos, waiting for the next generation of explorers, thinkers, and dreamers to listen. Imagine for a moment being near that edge. The universe behind you is a blur of fast-forwarded starlight. In front of you, there is only the placid, perfect dark. Time slows. Each beat of your heart, a slow, deliberate drum against the fabric of a second for you could be a millennium for the rest of the cosmos. In that deep quiet, what would you think? What would you feel? You are at the final boundary, not just of space, but of knowing. And that's where we'll leave our journey for now, not with an answer, but with a feeling, a sense of awe for the scale of it all, and a quiet respect for the mysteries that remain. The cosmos doesn't owe us simplicity, but it offers us endless wonder. Thank you so much for joining me on this incredible voyage. If this series sparked your curiosity, I'd be honored if you'd like this video. Subscribe to the channel, and perhaps share a comment below. What questions do black holes leave you with? What myths or stories do they bring to your mind? Our exploration doesn't have to end here. There are so many other wonders to visit: the city-sized density of neutron stars, the explosive birth of cosmic inflation, the very first moments of our universe. Until our next journey together, keep looking up and never stop asking why. Thank you for watching.